Failure. Termination of the ability of an item to perform a required function. Reliability is the probability that an item of plant will perform its duty without failure over a designated time. Reliability is the chance of completing the mission. Failure mode dominant, manner in which an item fails, theoretical focus, historic failure or experienced event. The effect that you see when an item fails. Failure modes can be electrical, open or short circuit, stuck at high, physical, loss of speed, excessive noise, or functional, loss of power gain, communication loss, high error level. Failure effect, consequence of a failure mode on the operation, function, or status of the item. Failure mechanism, the processes by which failure modes are induced. It includes physical, mechanical, electrical, chemical, or other processes and their combinations. Knowledge of failure mechanism provides insight into the conditions that precipitate failures. Function, a verb-noun combination describing the purpose of a design. Requirement, a function performing with a certain characteristic. Failure site, the physical location where the failure mechanism is observed to occur and is often the location of the highest stresses and lowest strengths. Traditional bathtub curve in equipment life cycle model. The bathtub curve is a widely recognized graphical representation of equipment failure rates over time. It consists of 3 key phases: infant mortality, random failure, and wear-out, aging effect. This model helps in understanding failure patterns and implementing appropriate maintenance strategies. 1. Infant mortality phase. Characteristics: high initial failure rate, due to design flaws, manufacturing defects, improper installation, or early operational stresses. Failures tend to decline over time as defective units are identified and removed. Mitigation techniques. Burn-in testing, running equipment under controlled conditions before full deployment to detect early failures. Quality control, ensuring stringent manufacturing and assembly standards. Proper installation and commissioning, following best practices for setup and initial operation. 2. Random failure phase, useful life period. Characteristics: steady and low failure rate due to unpredictable external factors such as operational stresses, environmental conditions, and human errors. Failures occur randomly and are typically due to unforeseen defects or usage variations. Mitigation techniques. Preventive maintenance, PM regular inspections and servicing to catch issues before failure. Condition-based monitoring, CBM using real-time data, vibration, temperature, oil analysis to detect anomalies. Operator training and SOPs, ensuring proper usage and avoiding operational errors. 3. Wear-out phase, aging effect. Characteristics: increasing failure rates as components deteriorate due to fatigue, corrosion, material degradation, and prolonged use. Performance declines, and risk of breakdowns increases significantly. The reliability curves of Type A, B, and C are having age-related failure characteristics. Curve A, it is having a distinct wear-out zone. They have a constant or gradually increasing failure rate followed by pronounced wear zone. Example include reciprocating pump engines, pump liners. Routine maintenance, based on time, is effective. Bathtub curve, curve B. High failure rate at the beginning and end of the life. Infant mortality rate followed by constant failure rate and then pronounced wear-out. Example includes simple electromechanically systems, general machines. Slow aging curve C. Gradually increasing failure rate. Association with corrosion or creep. Generally process equipment in contact process products. Rebuild and component replacement tactics are effective examples. Turbines, pipes, refractory. The reliability curves of Type D, E, and F are having random failure characteristics and independent of the aging. Curve D is best new. Only age-related at the beginning of the life. A dominant increase in failures rate followed by constant failure rate on condition is the best maintenance approach. Example hydraulics and pneumatics. Curve E, constant failure rate. These are truly random failures and are not age-related. A constant failure rate throughout the life cycle of component routine age-related maintenance is ineffective. Faux example ball bearings, complex electronics, and mechanical system. Curve F, infant mortality. Most likely failure rate a component would have is infant mortality, a high failure rate reduced to constant failure rate for remaining life. Once the infant mortality is resolved, routine maintenance is effective. Example include electronics and integrated equipment. Case studies show only 10% in aviation industries and 25% in ship industries. Components belongs to category of component having age-related failure characterizes, whereas the majority, if 90% in aviation industry and 75% OD ship industry, the component follow the random failure. Thus, age-related maintenance surveys or overhauls may not be as effective. Reliability of a series system. Example with motor mounting components. In a series system, the overall system reliability is determined by the product of the reliabilities of its individual components. If any one component in a series system fails, the entire system fails. Formula for series system reliability. Product of all individual reliabilities. As number of components increases, there is likelihood of decreasing overall reliability of system. Properties of series systems. The reliability of a series system can be no higher than the least reliable component. If k more items are added into a series system of items, say 1 added to a system of 2, each with R equals 0.9, the probability of failure of all items must fall in equal proportion, 33%, to maintain the original system reliability. 0.9 times 0.9 is equal to 0.93x. 0.93 times 0.93 is equal to 0.81. A small rise in reliability of all items, say R of the 3 items, rises 0.93 to 0.95, 2.2% improvement, causes a larger rise in system reliability from 0.81 to 0.86, 5%. Implications for equipment made of series systems. 1. System-wide improvements lift performance higher than local improvements. This is why planning, SOPs, training, and upskilling pay off. 2. Improve the least reliable parts of the least reliable equipment first. 3. Carry spares for series systems and keep the reliability of the spares high. For standardized components, so fewer spares are needed. 5. Removing failure modes lifts system reliability. This is why root cause failure analysis, RCFA, and failure mode and effects analysis, FMEA, pay off. 6. Provides pseudo-parallel equipment by providing tie-in locations for emergency equipment. 7. Simplify. Fewer components means higher reliability. Reliability of a parallel system. Example with dual power supply units. In a parallel system, the overall system reliability improves because failure occurs only if all components in the system fail. If at least one component remains operational, the system continues to function. Example, dual power supply units in a server. Consider a server with 2 independent power supply units, PSU, each having a reliability of 0.95, 95%. The system is designed so that if one PSU fails, the other can still supply power. The system will fail only if both PSUs fail simultaneously, which is a rare occurrence. Mitigation strategies to further improve reliability. Use more redundant components. Adding a third PSU would further improve reliability. Properties of parallel systems. The more number of components in parallel, the higher the system reliability. The reliability of the parallel arrangement is higher than the reliability of the most reliable component. Implications of parallel systems for equipment. 1. Use parallel arrangements when the risk of failure has high daft cost consequences. 2. Consider providing various paths for product to take in production plants with in-series equipment. 3. Build redundancy into your systems, so there is more than one way to do a thing. Truth hides beneath the surface. The unseen causes of motor failures. A motor may appear to be running fine until it suddenly fails. The real cause of failure often lies beneath the surface, hidden in small inefficiencies that go unnoticed. Small blue diamond unbalanced rotors. Small blue diamond misalignment. Small blue diamond poor lubrication, T. Small blue diamond blocked cooling. Small blue diamond bearing and seal issues.